Hear me? Is the mic working? Okay. Is it better? A little bit better? It's not sure. Is it better? Okay, so hello. Well, seems like it's a little bit. Okay, so today we're going to look at deep Q networks, and sort of we're going to look at some of the examples and some of the recent research that's been taking place in the space of reinforcement learning. So today we're just going to focus on Q networks, and then starting on Wednesday we're going to start looking at slightly different ways of training reinforcement learning agents. This would be using policy gradient methods. Okay, so just as a reminder, there are really three components to any reinforcement learning system, right? Policy, and that's the agent's behavior function, right? Remember when throughout most of the lectures we were looking at trying to estimate policy epsilon greedy or optimal policy and such. Value function, that's another big component, right? How good is each state and action? So for example, Q networks, that's precisely what they're trying to estimate. And obviously if you have a value function, you can get the policy out, right? And we've seen that. If I give you the value function, then you can basically figure out what the optimal policy is. And there is a third component, which is a model, which we haven't talked about much in this class. Later in the class, we'll probably look at some examples. And this is agent's representation of the environment, right? Most of the methods we've been looking so far are model-free reinforcement learning, right? We're not really modeling how environment is evolving over time. But in principle, if you have a good model of the environment, you can take that into account. So these are the three key components. A policy is the agent's behavior, right? So given in a particular state, for example, it really is a map from state to an action. So every time you hear the word, what's the policy, it really is, here's your state, what action you should be taking, right? And we've seen, we've looked at the examples of deterministic policies. Right, and there's also, in some cases, I think that in the next class, we'll see an example of where a stochastic policy might actually be the optimal policy. So stochastic policy is where you actually have a distribution of possible actions you should take, right? Now, so far in this class, we've looked at mostly deterministic policies. But if you remember when we were looking at exploration and just introduced the notion of epsilon greedy, right? So epsilon greedy would be stochastic policy because there is some probability of taking a different action as opposed to taking the most optimal one. Just a little bit of review so that we get back to the RL piece. The value function is really the prediction of future reward, right? So really, if you think about the value of the state, it's really saying, or the Q function, which is a function of the state and action, it really is telling you how much reward will I get from action A while being in state A, right? So Q function, for example, provides the expected total reward, right? So here's the definition of your Q function. You should know what that is, right? From state S and action A, so it's really a function of the state and the action, under policy pi, whatever your current policy is, which takes the action given the previous, given the state. And then with the discounting factor, this is the definition of the Q function, right? So it really is telling you the expected future discounted reward. Okay, and remember that from one of the first classes when you looked at the definition of Markov decision processes, the value function decomposed into Bellman equation. And that's a key decomposition for, and actually, as we've seen Q learning, for example, really relies on that decomposition. We've seen, things like TD learning, all of them pretty much rely on this decomposition. Okay? Now, the optimal value function is the maximum achievable value. Okay? So if you look at what's the optimal Q value, well, it's the maximum over all possible policies of the Q function under policy pi, right? So remember, different policies will give you different rewards. And the definition of the Q function is not the optimal one. It's basically saying what's the expected reward if I'm in state S and take action A and I follow policy pi, right? My total expected reward might be negative if my policy is really bad, right? But the optimal policy is if you take maximum of all possible policies. And that's the function that you're trying to learn, right? So once we have the optimal value function, action value function, sometimes called action value function, the agent can then act optimally, right? Once you have that, then this definition is pretty much, should be trivial, right? Basically, if you have the optimal state action function, then your best set of action would be to just take the action which maximizes this Q function, given in particular you are in particular state S. Okay? That's the optimal one. Now, formally, the optimal value also decomposes into the Bellman equation, right? So the optimal value, the optimal Q function, which is a function of state in action, also has this Bellman decomposition, right? Because there is an optimal under this policy, you can execute, you have a Bellman equation, but maybe intuitively you can think about informally, the optimal value maximizes over all decisions. So if you think about what's the optimal value function you're estimating, it really is the reward at the next time step you get if you take in action A, plus some discounting factor. You're looking at the maximum over all possible actions you should take at time t plus 1 so that you can get the most reward, right? Plus, the next time step, what's the action you should take so you can get maximum of possible rewards, right? So it's almost like if you're unrolling it forward, you're always trying to find the best rewards that you can get, right? That's sort of informal definition, and this is sort of the intuition, right? Yes?
Is this an updated equation or mathematical?
No, this is just the Bellman. It's just an approximation of the Bellman equation. Q star, and here's Q star. But remember, this is Q star at the state st plus 1 at the next time step, right?
Then Q star is defined as an max.
Yep. So Q star, this is just an informal decomposition. If you look at this expression is an equality, right? This is basically saying my optimal state is expected over the next state because it's probability distribution of possible states you can take, right? Of the reward at the next time step plus the optimal action you should take at the next time step. That's just recursive decomposition of the Bellman equation. This is just an intuition behind what the Q values are.
You call it informal because you're not doing this probability ponderation, right?
Yeah, because there is an expectation here. So you effectively has to take over possible because sometimes the environment is not really deterministic. Sometimes the environment might be stochastic. If I take the action, the state might be, one state, or could be another state, or could be another state, right? In many cases, if the environment is deterministic, given a state and an action, the next state is deterministic, then the expectation is just basically as one value. Okay, so that's the sort of informal definition of what the optimal value is. Again, you should think about the optimal Q value is it's sort of, if you unroll things forward, what's the best possible reward you could get if you start at a particular state and action and then you follow the optimal policy. Yes?
So in the last two equations, you can see why the last equation is right, but the equation before that, if you are locally choosing the maximum reward.
This one?
No,
this one?
Yes. That need not be the optimal value function. It should be the maximum action that would result in the the action that would result in the maximum return and not the reward.
You mean this one? This the last one?
No, the equation before that.
This one?
Yeah.
Yeah, this is just an informal definition. This is kind of like saying, because if you take the maximum, it sort of says that yes, you can, the next state doesn't necessarily have to be maximum, and the next state could be the maximum, because it's kind of like the long-term.
So the maximization is over the entire.
Yes, the maximum would be over the entire. This is just a simplification. Yeah, the maximum should really be over the entire possible future, right? This is more like a greedy way of doing it. So this is just an approximation. It's just a way. It's just a sort of a simpler way to think about it, right? Which is at every single time step you're trying to get the maximum. But by this definition, yes, you want to get the maximum reward in the entire rollout. Yes, that's right. Yep. But this is sort of an informal way of thinking about it, what the Q value is, just on the intuitive level. Okay, so these are the optimal value functions. Now the model, there are approaches, again, we're not going to look at these approaches in this class, but there are approaches for trying to learn the model from the experience. It's actually trying to learn, for example, the dynamics of the world around you. Right, which effectively is trying to learn what's the distribution of the next state given the previous state and the action that you're taking. So you can, basically, if you have a model of the entire environment, you can act as a proxy for the environment. Why is this useful? Well, this is useful because you can actually run simulations, right, once you have the model of the environment. And you can also interact with the model. For example, you can use look-ahead search, right, to try to figure out what's the optimal trajectory. You can do planning and such. Now, in practice, depending on which problem you're working on, actually building the model of the experience is actually a very hard problem. And again, we'll look at some of those examples later in the class. But in this class, today we're going to focus on model-free approaches. Okay, now, let's look at an approaches to doing reinforcement learning, right? So far, in most of our classes, we've looked at the value-based reinforcement learning, right? So for example, we were trying to find or trying to look at the optimal value function Q, right? And remember, we've looked at, Monte Carlo estimates, TD learning, and so forth, right? All of these approaches are trying to estimate the Q function or try to estimate the value function. Once you have the Q function or the value function, you can get the policy out, right? And this is the maximum value achievable under any policy, right? So, and remember, we had the examples where we try to estimate what the value is, and then we would try to greedify the policy. And then again, we estimate the value, try to find the greedy policy, and so forth. So the loop of estimating and then re-estimating the policy. So this is called the value-based approach. Now, the second class of algorithms that we're going to study in this class are the policy-based reinforcement learning. And these models, they're trying to search directly for the optimal policy pi. And this is the policy achieving the maximum future reward, right? So instead of, we're going to be bypassing estimating the Q function, but we're going to be trying to estimate the policy directly, right? And sometimes it makes an intuitive sense, right? If you know nothing about RL and you say, I want to build a robot, the robot sees the environment and then it spits out the probability distribution of possible actions, like turn left or turn right. And if the robot is wrong, then you're updating through some kind of update what the policy should be, which basically says, don't take this action, take this action, right? And so these policy-based reinforcement learning algorithms can actually work quite well. And actually, there are also classes of models that we're going to look at that combine value-based RL and policy-based RL. So you're learning both the value function and the policy jointly. And then there is, again, model-based reinforcement learning, which is you build a model of the environment. And you can plan, for example, by doing look-ahead. Remember, like one of the first classes, I think even like the second class, you looked at dynamic programming, right? So dynamic programming requires you knowing what the model is. Once you have the dynamics of the world, you can actually precisely tell what's the distribution of possible states given the previous state and the action that you've taken. Then you can sort of do planning and you can do look ahead using the model. Yes?
If it is so trivial to get the policy out of your value function, like if you have Q star, the policy is just the argmax. So what would be the difference between like?
Yeah,
and
good question. What's the difference between these two? These are just two different approaches. We're going to see that in some cases, this estimator can learn faster. And sometimes it's more desirable. In fact, some of the models, some of the more successful models are combining both. So we're going to look at models based on actor-critic type of models that actually do combine both. So we'll see advantages and disadvantages of both. Yes?
So given the policy, you can also calculate the Q star, right? I'm just like trying to do it.
So if you have the policy, yes. If you have the policy, you can basically simulate forward and estimate what the value of the state is. So they are all related, right? In many cases, if you think about this approach, in many cases, the reason why this approach has become popular in the last decade is because what people actually do, and again, we're going to look at these models, is we're going to look at parameterizing policy by some parameter theta, and actually use gradient descent algorithm to find what the theta is. And that actually creates, it makes it much more efficient to find the right policy. Now, there are also problems is that once you do approximations and so forth, can you reach the global, can you reach the optimal policy? Then it becomes a little bit tricky. But in general, the whole idea, and in today's class, we're also going to see that we're going to parameterize Q with some parameters, and we're going to learn what the Q function is. In many cases, the other important thing to differentiate between these two approaches is that, remember when we looked at the Q learning, in many cases, the optimal policy is deterministic, right? Once you have the optimal Q function, the optimal policy is deterministic. But there are some examples where the optimal policy is stochastic. So in other words, you want to have a distribution of possible actions. And that's where policy-based reinforcement learning comes in as well. So you can do that. We'll see some examples of that in the next class. Yes?
Could you just elaborate what's the second category of approaches? Is policy by iteration this or?
No, so here you're directly going to be finding the optimal policy pi.
So that's what we're doing policy iteration there.
Policy iteration, you're sort of like trying to find the value and then re-estimate the policy. And again, you estimate the value and you estimate the policy. Here you basically say, forget about the value. I'm just going to be optimizing policy directly. So we're going to see some examples of that. They're all very much related to each other. So sometimes it can be confusing what's one versus another. But we'll see examples of both in the next class. So in today's class, we're still going to be focusing on the value-based reinforcement learning. So far, for just and particularly on Q learning. Okay. Okay. Now, deep reinforcement learning. It's basically trying to use essentially deep neural networks to represent value function, perhaps to represent policy, or perhaps to represent even model, right? So far, the most successful stories have been kind of trying to approximate the value function and the policy using deep neural networks, right? And the whole idea here is we're going to be optimizing some loss functions that we're going to define by using stochastic gradient descent. And I'm going to make it more precise, but that's the idea. You're formulating these problems as optimization problems, and you're optimizing over the parameters of a neural network. Okay, so deep Q networks. This is something that came out in the last few years, I think in 2013, 2014, it actually works surprisingly well. Nobody expected these models to work so well. So what we're going to do is we're going to represent the value function by Q network with weights W. So we're going to be saying the optimal Q function is going to be approximated by basically a deep neural network with parameters W. Okay? And here's the way of optimizing. Now, in this case, we're just going to be focusing on settings where your actions are discrete. Okay? So, I guess you can do both ways. You can have a system which takes a state and an action and produces a Q function. That's one way of doing it, right? So if given a state and given an action, you have some neural network with some parameters W that spits out the Q function. This is the approach that people have also used, particularly in a setting where you have discrete actions, which is you're given a state, the state goes through the neural network, and let's say if you have m different actions, you have m different outputs, one for each action. Okay? Because if you have, let's say, 3 actions, move forward, turn left, or turn right, then given a state, which say your visual field coming to the robot, and your output is just going to be 3 outputs, Q values for action 1, action 2, and action 3. And obviously, if you want to act optimally, you would take the maximum out of those. Okay? So it's 2 different ways of doing it, but this way has been sort of a little bit more dominant so far. So, Q learning. How is Q learning being done? So let's just revisit that again. So again, the optimal Q value should follow the Bellman equation, right? So what we're going to do is we're going to treat the right-hand side, this, as a target. Okay? And we're going to be minimizing the mean squared error by stochastic gradient descent. So let's look at this expression. This expression is essentially saying that this is your target, and this is, this is what it should be, because that's roughly an equality, right? And you're trying to minimize L2 distance between the two. Okay? So what's the intuition behind this decomposition? Oh yes, question.
So when you say gradient descent, you're taking the steps in the W space?
Yes. You're going to be taking steps in a W.
What you said, S prime too?
S prime is given to you, so I'm going to make it more precise what it is. Yes. But let's look at this equation. What is this thing saying? What's the intuition? And what's the intuition behind this L2 loss? So let me parse this out. It's actually pretty intuitive. It's basically saying I want, L2 is 0 when these two are equal, right? And what is this saying? What is this saying? This Q value is saying what's the value of me being in state and taking action A? Well, me being in a particular state and taking action A should be the same as reward that I get at the next time step, plus, and what is this thing? This thing is essentially saying what's the value of being in state S prime, right? So if I'm in a particular state, I take action A, right? The value of this should be, the reward at the next time step. Most of the time it would be 0. Or, and then what's the value of the next state once I transition to that state, right? Does that make sense? Obviously, what this is saying, look, if your reward is bad at the next time step, your Q value should go down. But it's not just the reward, it's the reward plus the value of being in state S prime, right? So if I take the action, and at the next time step I get big reward, but the value of being at that state is also very bad, then my Q value should be small. Right? So for example, imagine that you have a robot standing and you're saying, okay, I'm going to move left, right? So you're moving left, you get some reward for being in that state, and then you see what's the value of this state. And the value of this state is really if there is a cliff on the left-hand side, maybe that's a very bad state to be in, right? So the value of being in that state and taking this action will be very small, or even negative, because I don't want to be close to the cliff, right? So it's a balance between the two things. When you think about when you think about supervised learning, in supervised learning there is only one target. Like did you classify cats correctly or not, right? Here it's really decomposition of the two. And if you remember when we looked at TD learning, this is an instance of TD learning, right? So these are the two things that effectively, and then at the same time, if you think about what's happening during learning is that, if let's say you play a game and you reach some state where you get big positive reward, let's say if you have huge positive reward, what's going to happen is that you're going to update the parameters of the model so that this one increases, right? And recursively, if this state increases, the state before will increase and so forth. So it kind of trickles down through the history. Yes?
The objective function is S prime a single state, or is that also the expectation?
So in this case, it should be an expectation. But for learning, it's actually a single state which is sampled from the environment. So in other words, in the standard Q-learning, you take a particular state, you take a particular action, the environment gives you the next state, right? And it gives you the reward at the next state, plus, and then you can compute what this is. Okay? One thing to remember when we looked at, we had a lecture on value function approximators. In one of the examples, we've looked at the minimizing the mean squared error between the true action value function and the approximate Q function, right? So we kind of look like what's the true value versus the approximation. Well, the TD approximation of the true value function is exactly this, right? According to the Bellman equation. So that's roughly where, if you look at the lecture, 3 lectures ago, when we looked at the value function approximation, this is exactly what we were looking at before. So this L2 distance is exactly coming from the approximations that we looked at before. And one of the interesting things about Q-learning is that these ideas have been around for like 20 years. Because people, instead of using deep neural networks, people use sort of linear function approximators, like take a bunch of features, take linear combinations, and then learn the parameters of the linear combinations, right? But the whole idea is basically the same. Whether this is, logistic function or a multi-layer neural network, two things are very similar. Now, you can minimize the mean squared error loss by stochastic gradient descent, and you can show that it will converge to the optimal Q value if you're using table lookup representation. So table lookup representation basically means that your state is discrete, your actions are discrete, so it's just one big table, right? And there are certain theorems you can look at, but it's basically saying if your state is finite, your actions are finite, and then you get optimal representation. And there's been a lot of work to try to see, okay, if your state is continuous, can you do some approximations and so forth so that you can still reach the optimal values? And there's a lot of work in that space. Like, can you have, polynomial time algorithm to find the optimal values and so forth, right? But if you're actually using a neural network to represent Q, then a lot of people found that it typically diverge. So training these models become very unstable, right? Because first of all, you have correlations between samples. Like if you have a robot and say, take action left, you're still kind of like in a similar state. Say, move forward, you move forward, but the state kind of remains the same. So obviously, as you're running things forward, samples from state action, reward, they're very correlated. So that's one. And the other problem is you have non-stationary targets, right?
What is table lookup representation?
Table lookup representation basically means that your state is finite, your action is finite. So the Q function is just one big table. States versus actions. It's discrete. Now, the other big problem is non-stationary targets. And remember, we've talked about this, right? It's almost like your parameters, you're changing your parameters. If you change your parameters, your target is also changing, right? And that's actually can cause instability in learning, right? So this is a setting where, this is your target, this is the network you're trying to optimize, but if you change double your parameters here, your targets will also change. So it's kind of an interesting system where, given you're in state action, your target is an approximation of what the true target should be. And that approximation depends on how good your Q function is. So if you're trying to approximate the output, you're giving a target to your neural network, but the target itself depends on the parameters of a neural network, right? And that causes instability.
What is exactly correlations between samples?
I'll get to that. So let's look at trying to solve this problem with correlations between samples. So one of the ways of removing the correlations would be to do experience replay. So imagine that you run the system forward, right? You start in state S1, you take action 1, you get the reward, you take state. Then again, state, you take an action, you get the reward, state 3. State 3, you take an action, you get the reward, you get to state 4. Obviously, these samples are going to be correlated, right? And the reason why they're going to be correlated because the states will probably not change a lot. You know, I have a robot. Imagine you have a robot and you say, okay, I'm in this state. This is my visual field. I say, you know, turn 30 degrees left. I'm turning 30 degrees. That's now my visual state. But it's very correlated with your previous sample, right? So that creates, if you're trying to, you know, learn for each row, it's almost like kind of training a neural network to say, you know, I give you 1,000 examples of cats, and learning the model just learning what the cats are, and then I give you now 1,000 examples of dogs, and you're learning what the dogs are, and you're forgetting what the cats are, right? So that's a problem with having correlations because the model just only looks at certain states, so they're quite correlated. And the idea behind experience replay is basically you're saying, well, I'm going to store all of these settings, and I'm going to sample experiences from data set and just apply the update. Very simple idea, right? It's almost like, you know, it's almost like natural when you're training your neural networks. You know, you have, let's say, 1,000 classes. If you're using ImageNet, you just randomize, right? You never put like all the cats in one thing, all the mushrooms in another batch, and sort of do that. So that's exactly the randomization that's taking place for training these models. Yes.
Or is the sampling uniform, or is it in proportion to, you know, how frequently you did an action?
So we'll get to that. We'll get to that. Right now, it's just uniform. Yes.
If you use so if you're doing batches, then that could be a problem. But if you used all the samples at the same time, every time you train,
Yeah. So generally, when you think about training these models, you never use the batch learning in general, right? You do stochastic gradient descent, which basically means you always, you know, train on mini batches. Right, so because in many cases these tables would be, you know, on the order of like, you know, 100,000, because you want to run your simulation forward, and so you typically train on examples of, you know, 100 or 200. In which case, if you randomly sample these, then the model is basically just saying, oh, if I'm in this state, I take this action. That's my update. If I'm in another completely random state, I take this other action. That's my target, right? So you're just randomizing over.
So is it feasible to do this somehow in an online manner?
It's tougher. It's tougher to do it in an online manner. We'll look at some examples later on, but it is tough to do it like online learning is much harder to do, precisely because you're inducing these correlations. So there are ways of doing that, but it's much tougher than doing it, you know, if you store your experiences. Yes.
So by sampling, you mean you're at each stage you're using some epsilon gradient approach to sample actions, or?
Yeah, that could be. Yes, that's right. It's going to be an epsilon greedy. To make it actually work, you have to use epsilon greedy. Yeah. Okay. Now to deal with non-stationarity, you're now decomposing this equation. That's another sort of modification you have to do. Notice that these parameters called W tilde, or, you know, there's I guess W bar. I don't know how to call it. It's W bar. So what you're doing is you're holding these parameters fixed. So the parameters of the target network, sometimes this is called the target network, these parameters are held fixed while you're updating the parameters of your Q network, right? So it's almost like you have two networks, right? So when you're updating your Q network, you're updating your Q network, but you're holding the W tilde fixed. And this is your target network. Now you have to resync them once in a while. And so there are multiple approaches people are exploring. You can resync them after every 1,000 updates, right? And just maintain. People sometimes use exponential moving averages, which is, you know, after 100 updates, you take 0.9 of old plus 0.1 of the new, right? So you keep it in sync somehow. But it's sort of, it's a weird thing because, you know, you're trying to optimize this quantity. It depends on WW. You want to take derivatives back to both. But this is much more stable because your target doesn't move. It just stays the same, even if it's wrong. So it stabilizes the learning dynamics. Yes?
So the target network is just the previous Q network, right?
It's what?
The previous Q network.
Yeah, it's a previous Q network. You can think about, you know, let's say after, like the simplest thing you can do is you can resync after every 1,000 updates. So for 1,000 updates, this network stays the same, and you're updating this network. So it goes up and down, changes its parameters. After 1,000 step, you basically say these two are now going to be equal. You start updating the next 1,000, right? And you can do smarter than that. You can do like moving average. Right? But it just stabilizes learning dynamics a lot. Yes?
Doesn't the Q value depends on what kind of policy you took to get the data? So it becomes like you have to, I don't know, like the data you're getting is actually
Good question.
a product of the value that you have. So
Good question. So why isn't Q depends on the policy that you're taking?
yeah, because it is bootstrapping the future into now. So it depends on the
Sure.
policy.
But is that? Any guesses? How many of you think it depends on the policy? Great. How many of you think it doesn't depend on the policy? Yes, it's a good question. If you look at it, it sort of doesn't really depend on the policy, right? The reason is the following. This Q is a function of state and action. Now, you have to choose your actions carefully, right? So, and that's why sometimes people use epsilon greedy to say, here's I'm in a particular state, I take this action. But the action could be uniform. It doesn't really have to be a particular policy, right? Because if you look at the update at the Q learning, the Q learning is just basically says, you give me state and action, the environment will produce the next state. And I don't really have to take the next action because I'm looking at the maximum of all possible actions. So it really is policy independent, right? So if you could uniformly take a state in action and just evaluate. For any state in action, you just evaluate, right? Given state in action, it doesn't require policy, right?
But for example, if you have a random policy in a grid and there are cliffs, the random policy are going to make the robot to fall all the time.
But the Q learning will converge to the optimal one, right? Because eventually you will figure out what's the optimal Q values are.
But then you need to like generate more data.
Yeah, you will have to generate more data, obviously, yes.
Oh.
Because ultimately, it's true that if you have millions of actions and some of them are right and many of them are wrong, then obviously uniform policy will do a lot of exploration because you're always going to be like doing the wrong things. But asymptotically, it will do the right thing as long as non-zero probability of choosing any one of those actions. Yes. So in practice, it's true. You sort of as you learn, you might want to. What people typically do in practice is that as the Q function learns, then you sort of the way you generate the data, you take the state, you run it through the neural network, you take the action, and you take most likely action plus epsilon greedy around it. So you're sort of inducing policy as you're learning your Q function. Yeah. Yes, question.
Is there a good criteria as how to choose a policy when you are generating your training data?
Typically, it's epsilon greedy. You start with uniform. Initially, it's like uniform because you don't know what the right actions are. As you're learning the Q function, right, you can use epsilon greedy. So you can sort of say, whenever I'm generating the data, I'm going to be using my Q function to mostly take the right action plus epsilon of taking uniform. And then you effectively anneal as you go forward, right?
Your policy in the process of
Yeah, because your policy here, if you think about it, what is your policy? Your policy here is like given state, pick the maximum action given the current Q value, right? But it's not necessary. If you just do that, you will not converge. So it has to be epsilon greedy. So initially during training, you basically your policy is uniform, and then you're kind of using your Q learning to figure out what the right thing is. And so remember, just as a reminder, remember when we looked at experience replay, right? This is just a slide from the previous lecture, which basically says that you want to create a data set, you sample the state value from the experience, and you just do stochastic gradient descent. Okay? This is just as a reminder for you to look back at the lectures when we looked at function approximators and look at experience replay. So deep Q networks, the two big points in a deep Q networks is that you have to use experience replay. That's important. Without experience replay, it's very hard to learn these models. So it's a practical thing, as well as fixed Q targets, right? And so how you're training these models is exactly that. You're going to be storing all of these transitions in memory. So given state, action, next reward, next step, you're going to be sampling a random mini batch of transitions, right? So you always sample a random mini batch. You compute Q learning targets. You compute Q targets with respect to old fixed parameters W tilde, right? And then you optimize this objective. So the targets here are being computed using old parameters. You still have to run it through your Q network to get this value. And now this now becomes the target. And that's it. That's the whole idea behind learning these models, right? So this becomes a Q target, Q learning target, and this is your Q network. And then you have to resync them once in a while, right? And these expectations, you think about what these expectations are, you're just sampling from your replay memory, right? And you just take the average. So typically, you sample